Okay, moving down to task number 2 with traffic load balancing, load sharing. Here we need to configure a require router to allow R8 to load share between R2 and R4 when it attempts to reach switch 1 loopback 10 through 12. And here we are allowed to use one new route distinguisher with the value of 200.201. Okay, so from R1, let's take a look right now. So right now when R1 is trying to reach, so right here, so traffic from R8 hits R1 and R1 sees the next hop for switch 1 to be R4. So you can see right here, and that's the only path that it has currently. So all these. So currently R1 takes that path. So what we want to be able to do is for R1 to have two paths. Obviously, there's a second path right here through R2 that R1 potentially can use, or R8 rather, since it's actually the originating traffic that potentially can use to get through to switch 1. So hopefully that R8 will be able to send traffic using both paths. But obviously right now R1 is only allow R8 to use only one path, which is through R4 to get to switch 1. So let me kind of explain why this is the case right now, because if you jump over to R3 and look at the output of the BGP table that we just did the show command on, you can see right here that R3 obviously know two separate paths to get to switch 1 loopback 10 through 12. You can see right here is either R2 or R4. Okay, but just because those two routes are tagged or prepended with a route distinguisher of 200, which is the same value, there are three basically things that these two routes are identical. So when it re-advertises that to the other PE devices, it just basically pick the best path. You can see right here with the greater than sign, thinks that the next hop to R4 is the best path, and it only advertised just one route out of the two to the PE device. That's why R1 is only see a single path to switch 1. So what we're going to have to do is to make these two routes unique from the R3 perspective, and the way to do that is to prepend the second route with a different route distinguisher. Okay, and that's why the task is telling us to use one new route distinguisher of 200.201. So we're going to pick VRF on R2, and we pretty much going to change the route distinguisher of that to 200.201. Okay, so let me kind of type that up. So route distinguisher for C2 is going to become 200.201. Right, so let's get on to the configuration. So IPVRF C2. First, we need to remove the existing route distinguisher, which is 200.200, and you're going to have to kind of wait for a few seconds here for the RD to be deleted. Okay, because if you go ahead and type in the new RD, which is 200.201, you will see right here that there's a warning message that deletion is in progress, and we have to wait for that to complete before we can re-enter a new RD value. Okay, let's try it one more time. Looks like I took it already. Just to be safe, let's do a show run and look at the router BGP just to make sure the configuration is still there. You can see that configuration for VRC2 is no longer there. We can try to do a show start and see if we can show that. So right here, when you do a show start, you can see address family IPv4 VRFC2, but when you do a show run, somehow VRFC2 configuration got wiped out in the process of the RD deletion. So we're going to have to put that back in. Just getting under router BGP 100, address family IPv4 VRFC2 with the network. Just advertise directly connected subnet, and then define the neighbor. So the neighbor for R2 is switch 1, and the IP of switch 1 facing R2 is 102.10, remote AS 65010. Next we'll activate, and don't forget we are using the same AS number for all of the VPN sites, so we have to specify the AS override option. Okay, now going back to R3, looks like the session came up right here. Going back to R3, do a show command. one more time, you can see now that we are seeing additional route distinguisher entries right here that belongs to switch 1 loopbacks. Okay, so we no longer have a separate path within the same route distinguisher anymore. So now R3 is seeing this particular routes as two separate unique routes. So when R3 advertises that to R1, they should advertise both sets of routes. Okay, and we can verify that by going back to R1 and do the show command. And it looks like we're still not seeing it, so let's do a clear IPBGP all. Give it a few seconds for everything to come back. And then we can try to do the show command one more time. Let's go back and double check our configuration on R2 on the VRF. Oh, there you go, that's the problem. We forgot to put in a route target. So obviously the router R1, the routes are not tagged by the appropriate route target, so the router R1 would not import the routes. So let's do route target 200, 200. This looks like route target got wiped out as when we deleted the route distinguisher as well. So now we're putting back the route target. Let's see, not sure if we have to clear a session or not. Nope, looks like it came through immediately. So you can see right now on R1 we did the show command. R1 is seeing two sets of routes for switch 1 loopbacks. One is pointing towards R2, the other one is pointing towards R4. Okay, but right now if you do show IP route VRF C2 10.10.0.0, you can see that in the routing table of R1 for that particular subnet, it still only have one route, and this is because by default BGP only use one route, which is the best path that it picks. So for us to allow the load sharing, we have to get under the router BGP IP address family IPv4 VRF C2, and then just like the traditional BGP, we use the maximum paths, and make sure you use the option EIBGP, and then we pick the number of paths to be 2 because that's all we have. And now if we go back and do that show command, actually before we do that, let's do show IPBGP VPN v4 all 10.10.0.0. So I have too many BGP. There you go. You can see how the route gets tagged with a multi-path at the end, although it's still saying that only one of the routes is best, but both routes gets tagged with the multi-path. That means if we do a show IP route VRF, we should be seeing two equal cost paths in the routing table. Okay, so also if you do show IP Ceph VRF C2 10.10.0.0, you see two paths that it can potentially load share the traffic, and you can see that the labels are unique for each path as well. Okay, we're seeing two labels again just because we are running MPLS VPN. So you got the regular topmost label for transport, and then the bottom for the MPLS VPN label. Alright, so that should complete our task number 2. Okay, next is our task number 3, is our final task as well, with a route filter and route target rewrite. Now using a route filter, configure R3 to prevent R8 from communicating with switch 1 loopback 12. So this is just a straightforward route filter that we're going to be performing on the route reflector, just because then now all the routes that's being exchanged between PE routers has to pass through the route reflector. So it kind of makes it easy to enforce a route filter. So on router R3, okay, there's nothing fancy about this. Just want to show you that the behavior of configuring a route filter and a route reflector isn't really different from a regular route filter. So switch 1 loopback 12. So we're gonna actually, let me show you right here. So we're gonna filter the route as R3 advertised to R1, basically block the routes of the switch 1 loopback 12. Okay, so IP prefix list switch 1 loopback 12 permit 10.10.20/24 route map, let's call it 2R1, deny 5, match IP address prefix list. So we can deny switch 1 loopback 12 and then permit everything else. So router BGP 100, that has to be performed under the address family VPN v4 tied to a neighbor R1, route map to R1 out. Okay, then as always have to do a route refresh with the clear IP BGP VPN v4 unicast out, AS100, and then out. Show IP prefix list detail, we get hit counts. We can go over to R1 just to make sure that R1 no longer received the routes. So here as part of the 1010, we do not see 1010.2 anymore. Okay, so it's been successfully filtered. And when you get onto R8, show IP BGP, and obviously R8 is not learning 1010.2 routes either. Okay, pretty simple for route filter. Next, we need to configure R3 to provide connectivity between Site 2 and Site 4, and at the same time disconnect Site 1 from Site 4. Okay, so we're not allowed to use any new route target, and we are not allowed to make changes on any PE routers. Okay, so the configuration only has to be performed on router R3, and the way that we're going to accomplish this is through a concept of route target rewrites. So at this point, we should have a good understanding of the whole concept behind the route target import and export. So basically, any PE routers can import any routes that has the particular route target attached to its routing tables. So the way we're going to accomplish this is currently Site 4 is tagging its route with the route target of 100. Okay, so in order to allow Site 2 to learn those routes, currently R2 is importing a route target of 200, 200. So we're going to have to rewrite the route target of, let me kind of do this. So 200 is what we're trying to get to, but we are coming from a 100. Okay, so that's in the direction coming from R2. At the same time, if you want R2 to learn the routes of the route that belongs to Site 2, we're going to have to rewrite the route because our Site 2 is exporting the route with route target 200, 200, and they have to rewrite it to 100, 100. Okay, so by doing that, it will automatically disconnect Site 1 from Site 4 because obviously Site 1 will no longer import the routes that's coming from Site 4 since the route target has changed to 200, 200, and Site 1 is only looking for 100, 100. Okay, and all these going to be done on the session between R3 and R2, so it doesn't really affect any other PE devices. Okay, so that's the concept behind the route target rewrites. Now we have to put that into configuration. So on R3, first we need to match the route target before we can rewrite it. We're going to use the extended community list. Just give it a number 1. And first we're going to match a route target of 100, 100. And then we're going to create another community list, number 2, that will match the route target of 200, 200. Okay, and just do a quick show BGP command and make sure our extended community list matches the routes that we want. We can apply the extended community list to the show command of the BGP and see what route matches that. So right now for the route target of 100, 100 or the extended community list number 1, these routes are the one that matches it. What we expected, those are the routes belongs to C1 VRF. And the same thing if we try to filter it based on extended community list number 2, we are only seeing routes that is part of the VRF C2. Okay, that's just a quick verification that we have correct extended community list defined. Then we have to create a route map, okay, to R2. So this is the one from the left to right. So it'll be this one right here. So to R2, permit 10. First we're going to match using extended community number 2 because we're going from 200 to 100. And then we're going to first delete it. So currently 200 is attached to the routes. So we're going to have to use the exact same community list. Let me see if I get this right. It's community, it's a little different syntax here. So number 2, and then the question mark, you can see that you can specify delete, although it's kind of counterintuitive because we use a set command, but there's an option to delete, so it's actually remove the route target from the routes, and then we're going to have to set it back, okay, with the route target value of 100, 100. Okay, and then we use the additive option as well. So the end result is going to be removing 200, 200, and then replacing it with 100, 100. And then make sure we allow everything else. So that would be permit 20. Okay, create a route map for the other direction. This time will be from R2, permit 10, match extended community 1, and then set xcom list 1 delete, and then set xcom xcommunity. Let's see, syntax a little confusing, so I kept typing in errors. So setting it to 200, 200 to replace the 100, 100, and then allow the rest of the routes. Okay, now we need to apply this towards 4. So router BGP 100, address family VPN v4, the neighbor 192.16, actually it's going to be towards R2, so it will be 0.2, route map to R2 out, and the other one will be from R2 in. Right, and you have to make sure we clear IP BGP VPN v4 in and out. Okay, next we do a quick test on R1 and see how R1 is now seeing the routes coming in. We show IP BGP VPN v4 all. You can see that now we have the R7 IP addresses show up as part of the VRFC2 right here. So we do show IP BGP VPN v4 all 7700. You can see that clearly the route target has changed from 100, 100 to 200, 200 right here. Okay, and it's complete replacement. We no longer see the original route target, which is 100, 100. Okay, and that's why it got successfully imported into the VRFC2. Okay, same thing on the router 2. Let's do a show IP BGP VPN v4 all. So we expect router R2 to see, as part of the VRFC1, to see all the routes that belongs to R8, which we do right here. And if we do the show command with 8800, we expect to see the route target to has the value of 100, 100, which is what we have rewritten the route target to, towards R2. Okay, now let's verify connectivity first from R6. So hopefully the site 1 is now been disconnected from site 4. So from R6, if you're trying to ping 7700, sourcing from loopback 10, you can see that it is now failing. Okay, we just show IP BGP. You can see the R6 is not even learning the routes that belongs to R7. Okay, now on R8, if you do ping 7700, sourcing from loopback 10, that is a success. If we do show IP BGP, and obviously R8 is now learning the R7 routes. Okay, same thing if you jump over to R7 and ping 8811, sourcing from loopback, let's try even 11 this time, and it's working. So show IP BGP, and R7 should be learning the route that belongs to R8. But not really to our surprise, we also seeing the routes that belongs to switch 1 coming across right here, and the reason for that was all the routes are now passing through the route reflector. So when R4 advertise switch 1 addresses to our R3, it also get caught by our route map that we configure towards R2. So that's why the route target for the switch 1 routes got rewritten as well to the value 100, 100, and that's why the R7 is seeing the route that belongs to switch 1 as well, you can see. All right, and that should complete our task number 3. As you can see, the route reflector in MPLS VPN environment is not a whole lot different from the route reflector with the traditional IPv4 BGP. Okay, you still only need to enable BGP on the PE routers, and the PE router still does not need to be participating in the BGP or even need to know the VPN routes, except if you want to use one of your PE routers to be a route reflector, then obviously that PE router will be learning all the VPN routes, although it doesn't really have to have all the VRF configured like the PE routers. The route reflector can pretty much be located anywhere in the network, and it doesn't even need to be in the path of the traffic. And for scalability purposes, you probably don't want your route reflector to be passing traffic, and just have the router dedicated for the BGP route advertisement. And also with the load balancing exercise that we did in this lab, probably give you a better idea the purpose of the route distinguisher as far as it making a BGP VPN v4 route unique, and usually becomes only significant when you use it with a route reflector, since you kind of lose the redundant path if you don't have a unique route reflector for each of the routes that's coming from different PE routers. Alright, so that wraps up our video on MPLS VPN with BGP route reflector. You can visit our website to view an extensive list of our lab videos and sign up to get access to additional lab contents. Thank you for watching LabMinutes.com, and I'll see you guys in the next video.